We are in the last stage to obtain the expression for the time evolution operator in the interaction picture. The differential equation satisfied by the time evolution operator in the interaction picture ui is like that. And we expanded the evolution operator in powers of v and made a perturbation theory. And we have obtained the expression that is a series expansion in powers of v. The leading term is identity, and next term is proportional to vi, integrated from t0 to t. And next term is v squared, order v squared. And the integral region is a little bit complicated. The first one, integral over t1, is from t0 to t2. And the second one, t2 is integrated from, again, minimum value t0 to the final value t. So there is some order. Okay? t1 runs from the initial to t2, and t2 runs from t0 to t. And t1 is always less than t2. That is one constraint. What happens to the nth power? This expansion can be related to the order n, and there are product of vi's of order n. The time t1, t2 to tn, and t1 runs from the minimum value to t2, t2 runs from the minimum value to t3, and so on. And at the final stage, tn runs from the minimum value to the maximum value t. We would like to sum these expressions, this series. But before we consider the whole summation, we would like to see what's happening in the second term. The great difference appears in the second term in comparison with the first order term. As I already told you, t1 runs from t0 to t2, and this is a plane of t1 and t2 variable of integration. Here, this is t2 and this is t1. t2 runs from 0 to t. t2 runs from 0 to t, and t1 is always less than t2 and always greater than t0. So I have chosen the origin to be t0, t0. Okay. So suppose I have t2. Given t2, I have given some t2. And what's the allowed value for t1? t1 runs from the minimum value t0 to up to t2. It never passes. So this is the line. This straight line is the line satisfying the equation t1 equals t2. Okay? So t1 is always less than t2 and always greater than t0. And this band runs from t2 equals t0, and it ends up with the value of t. So integral is made not in the square, instead in this right triangle. Okay? I'd like to simplify this integral in this way. So let us remove the over factor and just consider the integral. Over factor, just consider this integral, double integral only. I have t1 integral from t0 to t2, and t2 integral runs from t0 to t. Okay? And integrand is vi t2, t2, t1. vi t2, vi t1. V is a matrix, so they do not commute in general. Our constraint is that T1 is always less than T2. That means T2 minus T1 is greater than 0. This constraint can be constraint can be simplified by introducing a theta function. Theta function is argument. If the argument of the theta function is greater than 0, then its value is 1. If it is negative, then it is 0. So, why don't we release this upper bound of the integral to make it t? That simplifies the integral region symmetry. In order to do that, I have to introduce another factor here, remove any contribution that is coming from the value T1 is greater than T2, right? Then I should multiply this factor, theta T2 minus T1, right? Theta T2 minus T1 gives the value 1 only when this allowed region is approached, and if the integral, the value of T1 is outside of allowed region, then it returns the integrand 0. So now I have multiplied this theta function here, and I have released the upper bound T2 to be the maximum value T. So these two expressions are exactly the same, except that we have introduced the theta function, so argument of this integrand has been changed. Okay, so next step. We have VIT2, VIT2, VIT1 the same. I have theta function. If I write in this way, T1 and T2 are integrated out, and T1 and T2 are actually a dummy variable. T1 can be A or T2 can be B, something like that. So it's possible to replace 1 by 2 and 2 by 1, right? Because they are all integrated out. So just replacement has been made between 1 and 2. So I have replaced 2 by 1, 1 by 2, 2 by 1, 1 by 2, 2 by 1, 1 by 2. So this is exactly the same. Okay? Now the integral region is the same. I can flip the order. If I flip the order, then still the integrand is the same as the second one. This guy, the same. But I exchange the order of integration. That doesn't matter. The theta function automatically reorganized the integral to integrate only on the allowed region. Now, what I have found is that we have the same integral measure, the same integral region, but we have different integrand. Alright? But their value is exactly the same. The difference in here is this guy, T2 is always greater than T1. So greater value appears on the left side. Smaller value appears only at right side. Here, even though I have replaced the T1 by T2, the logic is the same. Even though it is T1, T1 should be later than T2. That means that T1 interaction appears later than T2, right? Or T1 is greater than T2. That's right. Vi with a later time appears always on the left side. So at first glance, these two integrals look different, but they are actually the same. So why don't we add these two to symmetrize the expressions? And if I add these two, then I have to multiply 1/2. Then that is the same as the original value. If I extend this method to higher orders, for example, if I have the three products, the product of the three potential, then I would have 3 factorial cases. T1, T2, T3 should be ordered with 1, 2, 3, and so on. And there's a corresponding theta function must be multiplied there. Alright? Alright. Then I sum these two and divide this sum by factor of 2 factorial. So the original integral of v squared from t0 to t2, where is the original one? Here. t0 to t2 and t0 to t, right, is now expressed as 1 over 2 factorial integration of t1 and t2 from the minimum to maximum, right? And sum of these two pieces. The VV, easy to remember. The way to remember is that later time. If T2 is greater than T1, Vi with T2, greater value must appear on the left side and smaller value appears on the right side, right? And if T1 is greater than T2, then T1 is later than T2, so T1 appears on the left and T2 appears on the right. Alright. So logically it is easy to generalize this result to the n power of n. Then I have 1 over n factorial, and there are various theta functions to define the permutation of 3 times and Vi, T1, T2, T3, and so on. So let us define time-ordered product of 2 operators. If there is a product of 2 operators, T1 at T2, time-ordered product is, if T1 is greater than T2, then the left one, A, appears on the left. If T2 is greater, then this guy appears on the left, right? As we have used the theta function to satisfy, to simplify these expressions, we can rewrite this definition in terms of theta function. The time-ordered product of AT2 BT1 is AT2 BT1 with T2 is greater than T1. And exchange the order, if T1 is greater than T2, okay, we have theta function, theta T1 minus T2, then T1 and T2, they must be one of them must be greater than the other. Sure, it's possible to have the same value. In that case, it is the integral measure is just 0, so it doesn't contribute at all. So it's enough to express in this way. Okay. Then, why don't we make use of this definition, time-ordered product, to re-express this? Alright. Just substitute Vi to A, Vi to B. let's see what happens. A is vi, b equals vi. Let us copy these whole expressions one more time, and then replace a by b, b by b, a by b, b by b. Alright. This term is identical to this term. This term is identical to this term. Okay? Therefore, this integral is a 1/2 factorial time ordered product of VB. Right? Because this whole thing is time ordered product VI, T1, VI, T2, right? And then this can even be simplified T0 to T1, T, dt2, VI, T2, T0 to T, T1, VI, T, VI, T2, T1. And I have time ordered product outside, right? As I already explained, this method can be generalized to find that the order n integral is 1/n factorial of time ordered product of this integral, running from t0 to maximum value for all integral variables, right? Then, these series expansion can be simplified as a summation of over factors of order n divided by n factorial, and all those integrals are expressed as the time ordered product of the integrals of power n. And then if I put this time ordered product operator outside of the summation, what I get is just exponential. Exponential minus I over h bar integrated from t0 to t of what? Interaction pictures potential energy. So this is ui. ui t0 to t is expressed like that. And this guy satisfies at all orders in V. This is complete relation. So interaction picture is very useful to find the evolution of interaction state, and the state function in the interaction picture is evolving with respect to time with this operator. And T is the time ordered product. For the case of two operated product, time ordered product is like that, and it is easy to generalize to n order n operator. Okay, so in the next class we will extend this method. We will apply this method to reproduce the Fermi's golden rule.